Hey, hello, my name is Brian, and this is my lab 2 motion of a falling object. The object I used was a hat because I feel like it would be a great visual model that experiences both drag and gravity. And yeah, I feel like the inside of a hat obviously has a lot of drag and resistance to it, so yeah, I chose the hats. The model for the gravity only, um, it shows obviously one force acting upon on the object, right? Gravity pointed downwards, and as you can see, it just the position versus time graph shows that it just accelerates downwards, and it does that for all models, obviously, but this one does it faster, as you can see from the calculations. I use the delta x equals v naught delta t plus 1/2 a delta t squared. Of course, we know that the initial velocity is zero, so because it was released from rest, right? So yeah, we have a delta y that is negative 3.14 meters, right? And that is also displayed, illustrated by the graph here. And yeah, because only gravity is acting upon it, our F net here is only Fg. Now we go on to the model where we introduce drag. Right, drag is pointing upwards, opposing the direction of motion, and of course that's going to slow down the object. All right, in theory. So obviously, instead of going to negative 3.14 meters, we only have what about negative 2.2 meters, right? Or it takes much longer to reach that negative 3.14 threshold. The model for this model, I use b equals zero point 0.1, which is very small, but also considering that I did this in my room, where the air resistance is almost negligible, I think it's pretty accurate to say that b could be very low, right? The constant. The F net is going to be FD minus FG, right? Or FD is standing for F drag, right? Obviously, because from the force diagram that we've seen, the drag is pointing in the positive y direction, and gravity is pointing in the negative y direction. Um, and for this case, because the object wasn't falling for long enough, right? Maybe also it wasn't fast. Also, the air resistance was negligible. You could say that gravity had a greater magnitude than drag in this case, right? As you can see by the hat accelerating downwards at a fast pace. And yeah, this graph here just shows that, right? It's accelerating downwards at a fast pace, for zero point 0.8 seconds. Um, I think the model on the right here, right, or the combination of the three models kind of just show that gravity, when only gravity is acting upon it, it's much faster, right? It reaches the floor in a very swift amount of time, right? Less than zero point 0.7 seconds, right? Whereas for the drag model and the experimental model, it requires all zero point 0.8 seconds to reach the floor. Think that the reason why the experimental position is a bit slower in this aspect is because I may have, probably due to human error, probably due to me adding an initial velocity to it, right? Thus increasing the drag. It could be that. Also, maybe the angle at which I dropped it on camera might have been off as well. But you could expect that the experimental model and the model drag, or the drag model, can show very similar, motion or flow of motion. What does this mean? I think for the velocity versus time graph, we know that it's going to be linear for the gravity only model because acceleration is constant, right? Negative 9.81. However, when drag is involved, I think it becomes dependent on the air resistance constant and the velocity. And you could see a very curved velocity versus time graph depending on, how big the drag is, right? And if it is big enough, it could reach what we call a terminal velocity, where the drag force balances out with the force of gravity, causing the net force to be zero. I think in this lab, it kind of just didn't happen, right? I think if you look at the graph for velocity versus time for the hat, I think it starts to like approach a certain value, but not yet. In the zero point 0.8 seconds that the experiment occurred, the lab just didn't reach that terminal velocity. Um, However, this is an example of what could happen if it is big enough. If the drag force is big enough, we have b equals zero point 0.9, of course, which isn't massive, right? But it is big enough to see that, oh, look, it does approach a certain value here, negative 1.6 or 1.7. So I think, yeah, if it is big enough, drag force is big enough, it could counteract the gravity. Also, because the hat didn't weigh much, right? The drag force doesn't need to be that humongous either. So what if the object was thrown down? That's another question. If you have an initial velocity of negative vi, right, then we also have initial drag, right? We have increased initial drag. For this case, the velocity versus time graph is just shifted down because, again, we never reached that terminal velocity, right? However, I think in certain cases where the resistance is big enough, and maybe the initial velocity is also big enough, then that terminal velocity will, it will be there, right? But it doesn't change, all right? No matter where the initial velocity is, it still approaches the same terminal velocity. And this just these two graphs show it, right? You have an object from rest here, and an object released at with negative 2.8 meters per second. Um, no matter what, they approach the same value, right? Terminal velocity is just a point where the force of drag, right, meets the force of gravity, right? So that's kind of just where the terminal velocity is, and no matter what the initial velocity may be, it will approach the same value. All right, that was it for me. Thank you.